Good evening, everyone. Thanks for coming this evening. Marcus and Geoff are going to give us a talk on teleconnections and how they affect the water resources in the east of England. First things first, the usual set of slides, although it's not moving to the next one. Arrow keys aren't working, there we go. Just a few things about first aid. If you need any assistance, please just contact one of us, either me or Berna. And fire procedures, we are not expecting a fire drill here. So if you do hear one, please do leave the building by any means. Just a couple of things about RMET's membership. So here is a list of some of the benefits of membership to RMET's. So you get the in-house journal, weather, and free online access to the full journal portfolio of titles, including the quarterly journal and the International Journal of Climatology. You get exclusive monthly members newsletters with the latest news and events from the Society and discounts at conferences for paid-for meetings. You also have access to support grants on there, so it is definitely worth even students signing up to RMET's if you can. And for those in careers, RMET's are the accreditation board for registered and chartered meteorologists. These have different experience levels, starting with RMET's after 3 years of operational experience and then chartered a bit later in your career. But these are the highest levels you can receive from RMET's and accreditation from them. But yeah, I'll hand over to Geoff and Marcus.
Awesome.
Brilliant.
Thank you, James. And yeah, thank you everyone for coming today. So we're here to talk about teleconnections, what they are, some well-known ones, and what they mean for water resources in the east of England. So starting off, the UK climate is classified as a mild maritime climate. This is mainly due to the Atlantic Ocean and the North Sea. We are an island after all, so we are dominated by weather from the surrounding sea and ocean. And actually it's the sort of the Atlantic meridional overturning circulation, that's always a mouthful. The AMOC is actually, it flows from the Arctic all the way down to the Antarctic. So yeah, there's this large overturning circulation in the Atlantic Ocean, which is basically from the Arctic to the Antarctic, and as it comes back up, it's, let me just get my laser pointer. It sinks in the Arctic and is on the bottom of the ocean, and it rises in the Antarctic and warms up, and so we get a lot of warm water from this Gulf Stream here, from the sort of Tropic of Cancer. So that brings a lot of warm water in this circulation. So that brings milder maritime weather on that aspect. But also we get it from the jet stream here, which is why we normally get westerly winds throughout the year. So overall, there are 6 different types of air masses that drive our weather, depending on the pressure pattern that is directly over the UK at any one time. So these westerly winds from the jet stream normally mean that the most common air mass types come from the Atlantic. And so this often brings rain due to the warmer, milder ocean on that side. So that's why we get a lot of sort of storms, as I'm sure you guys have noticed in the past few months. We've had, Storm Dara, for example, coming from that sort of westerly area. And due to the location of the jet stream, mainly we get these two here as opposed to tropical maritime air mass. So these two, the polar maritime and the returning polar maritime, are the most common air masses we get over the UK. So for rainfall across the UK, there is a very obvious and prominent pattern. So you can see the orographic effects of the mountains in the west. So this is where the air is uplifted by them, the water condenses, and then it cools and falls as rain, which removes this moisture for the rest of the land afterwards. And so for the east, as you can see here, it's very, very dry. However, it is impacted mainly in the east by surface heating, also known as convection. And so the ground in summer, as it heats up, more moisture is driven up by that warm surface, and therefore you get more rainfall, as you can see here and here, in summer and autumn, as opposed to winter and spring. So specifically for East Anglia, it is one of the driest regions of the UK, if not the driest region, with annual values of around 600 to 750 millimetres. The driest period of the year is spring, and the wettest is from October to December. One thing to notice here actually is August. So you can see that August has quite a large rainfall value, and this is again due to that sort of land convection. As you know, ploughed fields that are bare soil, they warm up quite a lot, and so as moist air is drawn across the UK and gets heated by these fields and the land, it then creates very, very heavy thunderstorms. This does mean, however, that some areas of East Anglia are, will get these thunderstorms, whereas others won't. So it's extremely localized, and you can actually see that on the map here. So like some areas of East Anglia are much drier than others, and so you can see North Norfolk, which is just here, is actually a bit wetter than the other areas of East Anglia, and this is due to sort of showers coming off the north coast, that sort of stuff, and dumping the rain that way before it gets any further inland. So there is a sort of spatial distribution of rain across East Anglia when it comes to that sort of thing. So now into the meat of the presentation. So what are teleconnections? So first of all, there is a massive, huge system, wave as you call it, called Rossby waves. So they're giant meanders in very high altitude winds, and this impacts the sort of global surface pressure. So it goes down through the stratosphere, troposphere, right onto the surface with atmospheric surface pressure. And so these sort of synoptic, very large synoptic areas can be collectively known as teleconnections, and they often have oscillating positive and negative phases, and they're normally described either by atmospheric pressure or sea surface temperature anomalies, and that allows us to see what phase they're in and how strong they are, that sort of thing. And so the location of these patterns matters a lot in terms of their impact towards the surrounding areas. So let's start with a couple that are quite close to home. So the North Atlantic Oscillation, I presume quite a lot of you will know what this is or have heard of it at least. It's basically the measure of pressure difference across the North Atlantic Ocean, and it helps drive these sort of westerly winds that we see over the UK. So in the normal state of the atmosphere, there's higher pressure over the Azores and lower pressure over Iceland. And so we measure the phase of the North Atlantic Oscillation based on the difference in pressure of these two systems. So during the North Atlantic Oscillation's negative mode, which is here, pressure over the Azores and Iceland, the difference is relatively small. So there's not a very high pressure over the Azores and not that low pressure over Iceland. And that basically means that you get this weaker jet stream, which becomes a lot more sinusoidal, and otherwise known as meridional is what we use in meteorological terms. And during its positive phase, the Icelandic low is much, much lower. So you can see on the right-hand side here, this is much lower pressure over Iceland, and as well as over the Azores, you have a much higher pressure. So this increases that pressure difference, which basically strengthens the jet stream and makes it it drives a lot more storms into or over the UK. And so you can see here that generally speaking, when the North Atlantic Oscillation is positive, the UK is more likely to see storms and rainfall. In its negative phase, it's more likely to see sort of high pressure blocking over Europe, which stops some of these storms from reaching us. I would just add though that even though the NAO can be positive, it therefore means more rainfall and storms will come across the UK, it can actually still lead to drier weather in the east of England, and it's all dependent on where that sort of storm track is. And this storm track can be seen as this black arrow on these bottom two pictures here. So in its negative mode, there's a nice block over Europe, and it can drive storms either further south of the UK or even further north. And during its positive mode, you can see that this storm track is quite heavily directly over the UK. So the next global teleconnection is the Arctic Oscillation. And so this is heavily linked to the NAO, and it's measured by the pressure anomalies in the Arctic and the northern parts of either the Pacific or the Atlantic Oceans. So on average, the pressure over the Arctic is much lower than the pressure anomaly above the Pacific. And during a negative phase, this pressure anomaly above the Arctic reduces, becoming higher than average. And so the opposite occurs over the oceanic basin, it becomes lower than average. And this leads to, again, a much more sinusoidal sort of meridional effect, allowing this cold air to sink down into the lower latitudes. During its positive phase, the surface pressure above the Arctic is lower than average, and the pressure over the oceans is higher than average. And this then keeps this jet stream much faster, much stronger, but also much tighter to the higher latitudes. And so this brings the jet stream further north effectively. And so that can control where this sort of storm track and jet stream can flow over the UK. And that compounded with the NAO has a really massive effect on the storm track and therefore our total rainfall over the UK. And because the Arctic Oscillation, it's basically a surface translation of what is happening up in the stratosphere, and specifically the stratospheric polar vortex. And sometimes interruptions in that and reversals and collapses can cause dramatic weather events, as I'm sure some of you and will remember back in 2018, the stratospheric polar vortex collapsed and then we had beast from the east, so a massive, huge blocking pattern over Europe and easterly winds, very, very cold, very dry period. And then finally, this is probably the most important teleconnection globally, the El Nino Southern Oscillation. And it's one of the most well-known teleconnections because it has such a wide scale knock-on effect. It has so many different indices, but mainly it is measured longitudinally across the Pacific Ocean, either with ocean surface temperature or surface atmospheric pressure. So the longest running of these indices is the Southern Oscillation Index, and this measures the pressure difference between Tahiti and Darwin, Australia. During a negative Southern Oscillation Index, otherwise known as an El Nino, waters near Darwin are much cooler, allowing dry air to sink and form a high pressure anomaly, providing settled weather for that region. Over the Central Pacific, this air is then warmed by the warm waters and it rises with moisture and evaporation, creates a low pressure anomaly, and therefore large convective clouds form here. The converse then happens during a positive Southern Oscillation Index or a La Nina. And so this sort of teleconnection pattern across the Pacific, and it impacts weather across the Pacific and beyond, especially downstream across the American continents, both north and south. It is also known that years with an El Nino tend to have higher global average temperature, and then the same with La Nina, they tend to be a little bit colder. So how do they all interact? I mean, there is as you can see from this rather scary looking graph down here, it is a very, very complex system of interactions between them. But obviously as weather is a very, complex system of interactions and flowing downstream, that sort of stuff, they're bound to knock on to each other. The top figure here shows the stratospheric pathway and tropospheric pathway interaction between El Nino and La Nina winters and how that impacts weather across Europe and the UK. The bottom picture here, that actually shows the network of sort of causal dependencies, so this knock-on effect from one teleconnection to another. And the thickness of each line here is the causality value. So the thicker means that it's more likely going to impact another teleconnection. And the colour is basically the sort of lag time in months. So you can see the light blue here is 1, so that'd be 1 month going up to 6 months. And then finally, these dots here, they represent, it's just their degree. So basically, Southern Oscillation Index and Nino 3.4, they're both measurements of El Nino Southern Oscillation, and they have they have a lot of interconnections and therefore are one of the most important teleconnections in the global state of weather. Right, I'll hand over to Geoff.
Thanks, Marcus. Yeah, brilliant. So this is the bit where we start to link it to water resources. And before we do that, I just sort of set out what the nature of water resources are like in the east of England. And I'm particularly focused on the Anglian water supply area. So within this area, we have 8 reservoirs. We have 6 direct river sources where we abstract directly from a river and put that water into treatment. And we have over 200 different groundwater sources, which are represented by those purple dots on the map. And collectively, the water from these sources are treated, and we supply that water via a large network of pipes to more than 5 million people. Now, an important feature of the water resources in this area is the size of the stores. And we're lucky enough to have large stores both above ground and below ground. So if we look above ground first, we have 8 reservoirs, as I mentioned, and collectively they hold over 220 million cubic meters of water. Most are what are known as pump storage reservoirs. So this is where we abstract water from a river. Typically they're from fairly secure abstractions in lower reaches of catchments. And we pump that water into a reservoir and store it until we need to abstract it for treatment purposes. But we also benefit from natural large underground aquifers, notably chalk, but also limestone and sandstone. And you can see those represented on the map on the right-hand side. So it's the chalk dominates in the east, for example, and the boreholes on their colours represent the different types of geology we're abstracting from, and if you're really eagle-eyed, you might be able to see the numbers on them, and that represents the level of vulnerability. So we know that some boreholes, for example, are more vulnerable to drought than others. But in general, these large stores make us fairly resilient to certainly short-term changes in weather. And related to this long storage, it means that large storage, it means that hydrological droughts in our region tend to have quite long lead-in times. Imagine if you've got a really, really big bucket and you're abstracting from that at a certain rate. It's clearly going to take you longer to deplete that bucket than if you just had a very small bowl, for example. And the same principle applies here. And what it means is that generally we have a rule of thumb that it takes 2 to 3 consecutive dry winters to cause significant resource issues in the east of England. And we know that from some of our theoretical modelling, but we also know that from practice. And on the left-hand side, you can see some snapshots of the rainfall and the deficits that led up to the situation that we faced in 1990 to 1992 in particular, which led to a severe depletion of groundwater within the region, and is really, from a groundwater perspective, our reference drought. And if you look on the right-hand side, you can see a plot of flow of the River Wensum here in Norwich. And again, you can see that it really takes successive dry winters in order to draw down river levels to a level that would cause us some concern. So at that point, I'm going to hand back to Marcus, who's going to talk a little bit about why we are focused on the winter half year.
Thanks, Geoff. So when it comes to recharging water resources and this sort of specific winter half year, the best way to show that is via precipitation minus evaporation. And so this graph shows specifically for the Anglian Water region, it's across the whole region, and so certain places might be worse off than others. So this is just the average across the whole region. So the winter half year can be seen in this red box. And so you can see over summer, more often than not, you are losing water resource in some form. You know, it is evaporating more often than not. And so you're heavily reliant on this period here where you get a lot more recharge. And so consistent years close to this minimum line can actually therefore compound and lead to these drought periods. And so this project was then completed only looking at rainfall within this winter half year, just so we could focus on this specific period. And so the droughts we used in this study was mainly from this list. So this is a list of multi-year droughts, and it was across the East Anglian region, and basically we included any October to March period within the dates seen here. So if any of the months October to March happened to sort of span this period, they were included in the study. So what do these droughts look like? Well, the average drought winter half year, which is a mouthful, but I have to say it so many times, still receives between 80 to 100% of the average rainfall. Although this seems like quite a high value, over many years, this can actually lead to a long-term drought. And actually, the driest parts of the Anglian Water region are the sort of the central and southern parts here, with Broadland and Lincolnshire being much closer to average. So this is probably due to the wintry showers coming off the North Sea, which gives some more rainfall to these two areas. And the decreased rainfall as well tends to occur in the October to December period. So you can see here these decreased values. It must also be remembered that this is only looking at multiple year droughts and not just specific years with reduced rainfall. So they have to be these long-term droughts. So linking it back to the teleconnections, which of these teleconnection patterns are most likely during these sort of long-term drought winter half years? And so what do their indexes and patterns look like during these periods? And so starting off with the North Atlantic Oscillation, the swing from negative to positive occurs much later and is much more extreme. So you can see that it starts off negative, much like a normal non-drought year, but it deepens into November, and then the swing is much greater, and so you're left with much higher values in January and February. For the Arctic Oscillation, it's positive throughout, but you can see there's this massive, huge spike in the Arctic Oscillation Index in February and March, as opposed to non-drought years where it's negative or close to zero throughout. And you know, as you can see here, drought years are La Nina, so they're a positive Southern Oscillation Index. That's a very strong signal to come from this drought year study, is the majority of droughts are in a La Nina year. So we also looked at two other teleconnections. These are sort of not as widely known. However, this is the East Atlantic Index. It's basically the North Atlantic Index in terms of pressure over two separate areas, but it's instead of a north-south type relationship, it's sort of east-west, as it sort of determines where the storm track is east and west, I'd say. And as you can see, much like a drought year, much like a non-drought year, it is all negative. However, there is a very, very strong period in March here where it's quite a bit more negative than a non-drought year. And also all the other years they are slightly more negative, but March is definitely one to sort of keep an eye on. And then the final teleconnection we looked at was the Atlantic multi-decadal oscillation. So this starts off positive and then becomes negative in December and then strengthens or deepens into March. However, looking at these values, you can see that they're incredibly small. So very, very small values. So we didn't disregard it, but it was, you know, we knew that these values were incredibly small, and that was taken into account. So to find out which of these teleconnections was the most important, a small decision tree was made. So this was made using thresholds of monthly values close to the average of all the separate teleconnections and using them as a filter for all years used in the study. So these average or close to average values can be seen in this table up here. After a statistical calculation, otherwise known as a Gini impurity, the bottom table was produced. And so here, smaller numbers indicate a stronger influence and should be considered as branches towards the sort of beginning of the decision tree. And it can actually be seen here that the two most important indices would be the strong positive Arctic oscillation and North Atlantic oscillation in February. So you can see there's a very, very obvious showing that February is very, very important for these teleconnections. Using these values, you can see that the reduced rainfall impact they have on East Anglia. In a year with a February Arctic oscillation value of 1.2 and above and a La Nina, the total winter half-year rainfall is reduced to 75%. And that's compared to the baseline average. As for the North Atlantic oscillation, so again, a La Nina year with a North Atlantic oscillation value of 2.5 or above in February, it leads to 87% of the average of the total rainfall. So this matches with the map from earlier. As you can see, you know, values around 80 or 90. But why is this rainfall reduced? So why do these teleconnections reduce this rainfall? So linking back to the previous slides, the Arctic oscillation and the North Atlantic oscillation, they heavily impact the location of the North Atlantic jet stream and therefore the storm track. As a positive Arctic oscillation causes the polar vortex to become more zonal and shifted further north, and a positive North Atlantic oscillation directly causes the jet stream to become more zonal as well. So they sort of add onto each other and it shifts this storm track much further north. So this rainfall then sort of batters, I'd say, like Northern Ireland, Northern England and Scotland, but leaves the Southern England and the east of England in the sort of rain shadow and without the rain. So this leaves the east of England in a very difficult chance for, you know, very little rainfall recharge to actually occur. So where are we now? I'll hand back to Geoff.
Brilliant, thanks Marcus. So I thought I'd just talk a little bit now about how we use this information, and to start with, what's the current situation that we're in? And actually we're in a very strong position from the resource perspective, and perhaps this isn't a surprise if we look back over the last few months and year even in terms of the teleconnections. But this is something that we publish on our website and we update once a month. This is the snapshot as of the end of January. I think you probably could go on now and get the end of February if my colleagues have had a chance to upload it. But here you can see what the rainfall was like in January, so fairly normal. And given the rainfall that we've had over the previous 12 months or so, and in fact we've had 2 reasonable winters in a row now, you can see that the resource situation is healthy. So our reservoirs are almost full, and actually the groundwater levels currently are in an above normal state. But this was very different to where we were if I'd been standing here 3 years ago, I would have been looking a lot more concerned. And it was those conditions in 2022 that led us to commission this work and other work in order to improve our understanding of that drought. But also we produced something, and we have to produce this, is by law, something called a drought plan, and we do that every 5 years. You can see the front cover of our 2022 drought plan on the slide. We're now in the process of updating that plan, which will be eventually published after consultation in 2027. And in that drought plan, it sets out both how we will deal with the drought and how we deal with an evolving drought as it gets progressively more severe. But we also talk about what we do by routine. So we continue to analyse things like rainfall, soil moisture, evaporation, groundwater levels, river flow, and aquifer recharge. And we have some heuristics which kind of help us with some of that, but we rely a lot on good quality data. And we monitor a set of early warning indicators based on standardized indices for things like precipitation, stream flow, and groundwater level. And more recently, we started using seasonal weather forecasts to undertake flow and reservoir forecasts. And what we do is we take an ensemble from the European Centre for Medium Range Weather Forecasting, a company called Earth System Data help us analyse that, and then it kind of goes, it's downscaled to the specific hydrological models that we have, and they are then reinitialised each month to produce our new forecasts. And what's interesting is we can start to layer on this additional kind of information about the teleconnections to give us some context for the 3-month forward look that we've got. And in 2022, it coincided really well. One of my PhD students, Wilson Chan, who's now graduated from the University of Reading, he was working with us, and as part of his PhD was looking at a storyline approach to drought and climate change. And what he did was he analysed numerous kind of possible winters for 2022. We first screened that for La Nina winters, and then we produced these possible futures, which is represented in the graph, which was a 4-way screening in terms of the North Atlantic Oscillation and the East Atlantic Index. So as Marcus has described, that gives us a pretty good guide to where the jet stream is above the UK. And from that, we were not only able to kind of confirm the analyses that Marcus has presented, in other words, dryness was heavily likely to be linked to a combination of La Nina, a positive NAO, and a negative East Atlantic Index. But also, we ran all of these scenarios through our hydrological models, and actually we were able to conclude that we were likely to remain in drought, regardless almost of what would happen over the first 6 to 9 months of 2022 because of the memory in the system. So the flip side of it being difficult to go into drought within the east of England is it takes longer to kind of come out of drought. And we were able to use this information to help with our operational planning within 2022. So I'm going to stop there and hand back to Marcus, who's going to just conclude by looking at whether we can really predict a drought using teleconnections.
Thanks, Geoff. So, can we actually use the teleconnection patterns, as I have shown, to actually predict whether or not this year will be a drought or this winter half year will have reduced rainfall? So after a dry spring and summer, it would be extremely helpful to see what kind of winter half year is approaching. And so each teleconnection has its own cycle and each vary with time. And so those with much longer timescales are much easier to forecast. So this includes El Nino Southern Oscillation. So it's a very, very long timescale in terms of its oscillation. So you can more easily predict where that will be towards, outwards of 1, 2, or even 3 months. Faster changing ones, such as the North Atlantic Oscillation and the Arctic Oscillation, are much harder to forecast. These can swing within 2 to 4 weeks very, very quickly. You can use sea level pressure forecasts over the Atlantic, and that can actually give you a sort of idea as to which way the North Atlantic Oscillation or the Arctic Oscillation will sort of swing towards. But they only normally go out to a couple of weeks, so can't really be used at the beginning of a winter half year to sort of predict what will happen in, say, February, the most, important month, as it were. As we know February is so important, efforts would be best placed to analyse this month specifically when in December or January, so you know what has happened before. So this is here. So to summarise, spring and summer, they've already been really, really dry. The most impactful winter half years start off in a La Nina. So if you know you're heading into the winter with a La Nina, you know it could be an issue. October to December, if they have had low rainfall, that's another tick in this sort of checkbox. And so December and January, that's the time to then look at the month ahead to see what these teleconnection patterns will look like in February. And so you can then also look at the past teleconnection patterns as well, add that to what you are predicting, and that should give you an idea as to how close to these drought winter half years you are currently having. And finally, what about climate change? How is this going to change teleconnections going forwards? Because this study was completed on historical data going back to, I think it was 1920 was the sort of year we started in the sort of study. But we know climate change is impacting our weather every day. There have been studies that suggest different teleconnections react differently to climate forcing being applied to them, and they will continue react into the future. So this graph shows standard deviation of the El Niño Southern Oscillation Index increase due to climate change. So therefore it's, much more intense, as it were, and it's increasing in intensity. And also climate change is effectively pumping more energy into the system. And it's very similar to, as the sort of cartoon shows, like pushing on a swing. So you're not only increasing the speed at which it goes from one to the other, you're also increasing the intensity of these swings. And so you can get very, very out of balance system quite quickly, and it can lead to extremely complicated and very difficult to sort of predict futures. More research, however, will be required to find out sort of specific effects of climate change on more teleconnections, that mainly concentrated on El Niño due to its sort of wide knock-on effects known throughout the globe. And so stuff like North Atlantic Oscillation, Arctic Oscillation, and even East Atlantic Index, there needs to be a bit more sort of study as to how climate change will affect that. Finally, thank you. Do we have any questions at all?
So, in the past, when I studied in America, there was a lot of chat about looking at analog years and looking back to, let's say, whatever setup you're kind of currently in at the moment. You look back for years that had a similar setup. Is that something that you guys thought about, or something that you potentially would want to look at? So, for example, if you know you've been in a El Niño for a certain amount of months and the NAO was a certain direction through this summer, what in the past has that meant for the coming winter?
So yes, is the short answer, but I think there's more analysis of the data sets that we could do. So it's interesting because the Environment Agency who sort of regulate this kind of space have started asking us to look specifically at La Nina years, having seen some of this kind of analysis. But what I think is particularly important for the east of England is that we would have to go beyond that. As we've shown, it's not just going to be simple enough to look at La Nina, El Nino, because the position of the North Atlantic Oscillation, the Arctic Index, the East Atlantic Index, they're all interconnected and make a really big difference on what we're seeing in the east. So I absolutely think it's a good technique, but we've got to kind of look at everything together.
I'll also add to that in this study we did look at the sort of weather patterns. So the Met Office, they release a sort of 30 pattern decider thing which looks at the surface pressure chart of a certain day, and they sort of put it in its own sort of relative pattern. And so we did look at sort of the most common of these weather patterns during these winter half drought years, and so that sort of allowed us to then compare it to, you know, when did these patterns also occur in different other years, that sort of stuff. So it allowed us that sort of comparison there.
And that's something that we're now looking at more. So we're alongside the 51 member ensemble seasonal forecast, we now have a view, again from our system data, around kind of like what the likely weather pattern dominance is over the kind of coming 3 months. So we're starting to try and sort of piece together the sort of intelligence from this kind of analysis into the kind of forecasting space. But yeah, we also need to look at that on a sort of broader timescale than just the forward 3 months for the reasons we've explained here.
Okay, well, my other question was around, so Geoff, you know that you've had one dry year, and you know now from the analysis that you guys have done that it's potentially a dry winter half coming up.
Yep.
What types of, is there kind of a top headline of things you would do differently at Anglian Water to be able to kind of address this?
Yes, it's a really good question, and it's always a judgment call around kind of when we start doing different things. But we have a trigger-based system. So if you take the reservoirs, for example, depending on what the level of the reservoir is for each month of the year, there's a set triggers that we use, and they might include demand management options. So we might put a temporary use ban or a hose pipe ban on for our customers. Obviously that tends to only be effective in summer, but we are also looking at sort of new behavioural mechanisms, so things like summer tariffs being different so you pay more in summer than compared to winter, as well as other kind of behavioural measures. But there may also be kind of supply side measures that we would take as well. So could we abstract more water from a river, obviously ensuring there aren't going to be environmental impacts in order to try and top the reservoirs up. So there are a range of things that we would do, but it is driven by the triggers and our forecasting of whether we think we're going to exceed or go below those triggers over time. Yep.
Right, so you mentioned just towards the end of the talk that there's some difficulty using the AO and AO because how quickly they can change. I was wondering whether you looked at MJO teleconnections as a way to kind of help boost that predictability in the next few weeks, or whether is it too kind of short time scale signals to really show up?
Yeah, so the MJO type connection, because sort of the generic flow of the Northern Hemisphere air is sort of coming from the west to the east, this type of sort of oscillation, the Madden-Julian oscillation, it mainly links with La Nina and El Nino. So that was one of the things, one of the pathways. I mean, anyway, if I go back, where is it? Here. So this sort of upward drawing of planetary waves, that comes directly from the Madden-Julian oscillation. And so that then pushes everything sort of downstream from that. So that has a sort of lag time, as it were, effect on weather over the UK. And so it's quite difficult to try and sort of use those in conjunction with lag times and that sort of stuff. And obviously with climate variability and the variability in just the weather, you know, any slight change that like upstream is gonna, or downstream is gonna then change exactly where it is sort of where over the UK. So it is very, very difficult to try and do that. You have to use models with, you know, so many different ensembles and stuff like that just to get a relative average picture of what it could look like. So it is quite difficult to do that, but yeah.
And second question, I don't know how relevant this is with kind of seasonal in pipeworks. How do you kind of work around that?
I mean, interesting question. It's just something. Unfortunately, with the data you've got, you just kind of have to use it. I mean, you can't try and. I mean, you could manually try to sort of correct it yourself, but that would then become an issue of like, is the correction you're making too much or too little? That sort of thing. So that can have an impact on the rest of the study as well, especially with something as important as El Nino. You don't want to sort of tamper with it too much in terms of how much of an impact it has for the rest of Teleconnections as a whole and how the knock-on effect is. But especially going into the sort of climate change aspect of it and way into the future, you know, the models can produce, you know, some of the best output there is, but no one knows for certain what exactly will happen and how these teleconnections will change. You know, no matter how many ensemble members you use, you know, how powerful the computer is, it's just, we don't know, unfortunately.
Yeah, I think there is a limit to the forecast on it, and I think that we have to acknowledge that. I think the other thing though is that it's back to what we were doing in 2022 was that actually if we kind of conditioned, and we were using basically a large reanalysis data set, and then we conditioned that or filtered it really into these 4 different kind of clusters, and actually then running the hydrological models based on those, we were able to kind of come up with some conclusions. So we weren't saying that one was more likely than the other, because although it was pretty likely that La Nina would persist for several months, there's a lot more uncertainty about what was going to happen to the other drivers. But actually, because of this memory in the hydrological system, we could draw some useful conclusions anyway. So that's quite a unique feature of our region that makes it a little bit more easy potentially to forecast the end state. But certainly from purely from a meteorological point of view, there definitely is a kind of limit, I think, to that.
Have you seen some skill with the seasonal forecast, or is it?
Well, the question is, have we seen some skill with the seasonal forecasts? Yeah, I think so. I mean, we haven't formally evaluated it yet because we've only kind of introduced it over the last couple of winter seasons. So we would really like to do some more work on evaluation. But they I mean, and again, we have seen probably more sort of typical winter conditions. So it's possibly had an easier ride, if you like it, from that point of view. But now, of course, we're shifting into La Nina again. So, I'm going to be particularly interested to see kind of how this winter looks and whether the forecasts are kind of getting that right. But there's a huge potential for more research in this area.
On the seasonal forecasting, was there any, what was sort of the background of choosing the EC? Obviously, there's loads of other season models out there. Was it just that was the only option that you sort of had, or was there any sort of, verification or extra thought that you've done on just using that one more than others?
Yes. So the question was around like why go with ECMWF for the seasonal forecasting. I mean, I think we did do some kind of comparison, but I think the easy availability of that data through the Copernicus type program made it very straightforward. It's a 51-member ensemble, which was attractive as well because we want that kind of plurality, if you like, in output. But yeah, there are other kind of systems that would be available. But I think certainly from the academic literature, ECMWF certainly stands up as a decent model. So yeah.
Are there any questions online? Do we know? Okay, awesome. Right then. Oh.
Thank you very much, guys.
Yeah, thank you for having us. Thank you.
Okay, so thank you everyone for obviously coming to the talk. We've got a couple of sheets over there, net zero sheet. It's just jumping ahead, good. We've got a net zero sheets and sign-in sheet. So I think most people have, but if there's 1 or 2 people that hasn't signed up, they're just over there, just next to James. it's all, you know, no one will know your postcode from that or anything. It's all anonymous stuff. It's just so that we can see how we're doing with the net zero sort of thing for our Mets. If there's any future topics you'd like us to talk about, that's me and James. Oh, what is that doing? That's me and James's email address is there. I don't know if it basically we're on LinkedIn and everything as well. We've got a Facebook page that will just be RMETS East Anglia. We post the talks on there, so you can see it's all on the RMETS website. So yeah, if there's any, like we're on LinkedIn, things like that. If you want to just message us, like, or connect with us, feel free. And yeah, we just want to try and find some talks that you guys are interested in, basically. So yeah, these are our next talks we've actually got. So last talk of the academic year is going to be on the 19th of May. So we're obviously skipping out Easter and everything. And that's just going to be basically 2 graduates who were at UEA possibly 2-3 years ago, that sort of thing. Basically working at the Environment Agency and also one of them works as an environmental consultant. So they're coming in and they're going to basically speak about sort of alternate things that you could do with an M degree. Basically, there's not so much to do with meteorology, but you know, there is still links there. So I think it would be just good to see alternative things you can do basically with your degree. So probably particularly good for students to come to if you know anyone else who's thinking, oh God, I don't know what I want to do with my, you know, life after this, and that could be a good one just to open a few, you know, more doors sort of thing. And then this is this talk for October 6th. This would be in our obviously next year, but it hasn't all been confirmed yet, but I think it's going to be on the 6th of October, and we're going to we've invited the president of our Mets to come in and speak with us. I'm not sure if that's going to be in person or online or both, so I'll have to see with that basically, but that's just an early thing of that we may have that talk basically coming about forecasting summer thunderstorms, so that one will be good. But yeah, that is everything.